me, it's very important that you follow day by day, and if you have any question, just ask me, because most of the time, if you hear my presentation or whatever presentation just without the context, without all the things that we are going to doing together, then maybe you miss the most important part. Okay, for that you will have the slides that I'm going to write during the classes. Okay, I'll give you the PDF. Okay, I'll tell you just in a second what I'm going to do. So books, okay, reference books. There are a number of reference books available for the transducer, for the measurements. Okay, so I'm not going to give you any advice about that because there are a very large number. So pick your best. The books are all very good books. For the regarding the strain gauge measurements, you have this one. Technology. And practical use. Okay, strain gauge. This is by Stefan Kiel. And is John Wheeler. Okay. Then we have model testing. Test user for strain gauges. Okay. Model testing from my friend Ewins. Waiting for the PC. Okay. Then I got the model analysis. Heat and food. Sorry for that, but I have to change the way. Info. Okay, and the other book is the vibration with control. And that is from another friend. Then random data. This is from Bender and Yusuf. Okay. During the break, I will change the fundamentals. Signal processing. This is sheet Hamno. The system notification. Notification from Pinterest. Okay, then we have some course notes, okay, during the semester. Regarding the way we are carrying out this course, I'd like to have you in the laboratory, okay, to have some tests. I plan about 4-5 test activities, okay. This will regard the use of the strain gauges, the model parameters of identification, okay, and signal processing. I'll give you a text or a problem to solve. I will emphasize some problems, some issues, and then you have to write your own report. Okay. The collection of these reports will be completed for your final exam. So that when you are having the final exam, one question will be on one of your final exam. Okay. Then another question will be on one item on the first part of the program, one item on the second part of the program, and so some curiosity about the program. Okay. The exam will be, has always been oral exam. Okay. Now, because of the virus, I moved to the written exam. So my oral question will be written by you during the session. Okay. So I don't know what happened, what will happen to your final exam in January, February, and so on, because it depends on the time regulation for the virus. So my history is that all the final exam will be oral. Okay. I'll pick one report. We will discuss the results and what happened to that report. Okay. And then we move to questions. Okay. For the virus, maybe those questions will be written. So you have to write and send me using exam.net or other platforms. You will have to send me your final exam, written final exam. I will read it and then I will for your approval. Okay. Um, uh, yes, that's it. Question. So softwares, I will make use of MATLAB. Okay, there is Sapienza student license and all that, so it's completely free. Um, I will use experimental test software that is from Siemens LMS because you don't have any hardware, so it is completely useless. Okay, but you will use that. Regarding the finite model analysis, I will refer to the Nastran code, but you can use whatever code. Again, if you're using the Nastran code, you have a student license available for you. Okay? You can use that without any other additional expense.
Professore, l'audio è molto disturbato, non sentiamo.
Okay. I think that we can have a quarter of an hour break right now. I'm trying to change the computers so that maybe we can have a smooth classes from here. Okay. So see you back in a quarter of an hour, say 3:15. Okay.
Professore, ci sente? Professore? Professore, ci sente?
perché qui
Mhm.
poi dopo io vado sotto, poi a un certo punto finisce, mi sa. Sì. C'era una cosa, però non la vedo più.
Questo
Inserisci, poi non fai niente.
ma invece questo
Vai.
dove era prima?
Qua, era su visualizzo disegni.
Questo qui cos'è?
Quello lì è il laccio.
Ah.
Il laccio.
Mm.
C'era qualche cosa, c'era. Non mi ricordo più. Che parte, no? Me ne dà un'altra, ma
È un altro file.
è un'altra file. È salita, è salita.
Cliccando i tre puntini cosa le dice? Quello di in alto a destra. No.
Eh? Cancellare, poi.
Servo di studio del telefono. Uno stage list, click last page.
No, ma questo è quello, eccolo qui,
Ah,
aggiungi,
ok.
ma è quello proprio del tablet.
Mm.
È quella la fregatura, guarda, questo computer che non funziona è un problema.
Pagina più,
Me ne
però
clicco,
fa l'altro file.
fa l'altro file. Vabbè, meglio di niente. C'è qualche cosa. Non me ne faccio tre.
E se invece fa ad esempio uno scroll a destra vuol dire una sorta di sfoglio pagine?
Vediamo. Non lo vedo prima, ecco. No, guarda.
Accidenti, questo perché è zoomato già. Prova a fare un volta pagina. Non so, prova. Come si torna? Provo. Che ha fatto?
Terminare la scrittura.
No, perché spesso i tablet con una scrollata verso destra o sinistra cambiano.
Sì, no, non l'ha fatta purtroppo. Vabbè, tanto l'ho fatto così, no, per il momento, poi me la studio.
Lui che cosa è apparso? Niente.
No, questa è la modalità vedi, vedi. Fa niente, mo lo va. Allora. Okay, can you see that? All right. I hope that you can hear me. Let's restart the class. Can you hear me?
Sì, professore, la sentiamo.
Okay. Yes,
Sì, prof.
Sorry for these issues, but it is because of the computer. Now I'm using a different one, so I hope that everything is okay. Once again, if you can't understand or if you can't hear me, just tell me so. Okay.
Professore, se non allontana il volto dal microfono del PC, la sentiamo, altrimenti non appena si allontana un po' iniziamo a sentirla a tratti.
Ok.
Quindi,
Questa è la
magari-
distanza, mi sentite? Da questa distanza mi sentite?
Sì, perfetto.
Okay. Okay, so let's recap the laboratory activity. What I'm planning is to have, as I said you before, some activities in the lab, and this lab will be with a group because you are a number. So please email me your actual capability to attend the laboratory. Of course, for those people who can't attend, I can arrange a different way. Maybe we can have a video recording of the laboratory activity or something like that. But if you can attend the laboratory, it is very helpful. You can see a lot of more things while you are there. Okay, so laboratory activity groups of about, let's say, 10 people. Okay, so that we can enter there and we have the right number of people that can do something. Okay, there is not a standard schedule about for the laboratory activities because it depends on the program. It could be considered on a, let's say, 2 weeks basis. Okay, so it could happen that we are going down the laboratory 2 in a month, more or less, depending on the status of the program. Then once again, I would like to divide you in groups, and maybe because you are all involved in classes during the afternoon, maybe we can do your laboratory activities during the morning. Okay, but it depends on you. So we can assume to have the standard class hours for the laboratory. So we can have 2 hours on Monday, these times, 2 hours on Tuesday. Okay, maybe we can have 1 hour on Friday, or maybe 2 if we can add 1 more hour there. Okay, and we are three groups. We can add 2 more time slots of 2 hours during the morning, for example. Okay, the week in which we are having laboratory activities, okay, there are no classes. Okay, so that your number of your effort is not increased that much. Okay, so that we can balance a little bit the times both for the laboratory activities and for the standard in-class activities. Okay. So having said that, I don't know if you have any question about how the course is organized in terms of exams, in terms of references, in terms of activities. Yes, about 10 people group. Yeah. 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 The idea is that once you are going down the laboratory for one activity, you will receive an activity text. Okay. For example, find the strain field of the structure, find the model parameters using these techniques. Okay, and so on. So for each activity, you have what you have to do. Okay, and then you have to write your own report about that. I will tell you how to write the report. The report should be the experimental activity. Okay, but I will talk about that later on. Okay, so don't it's not now the time to talk about that, but just for you to have an idea that you have to write a report, okay? So that at the very end, just before the exam, you have a collection of the report activities, okay? That is a starting point for your exam so that you know that I will ask something about one of these reports, okay? So you start studying something that you should know very well because it's the things that you wrote, okay? Well, and then we move on, okay, to other things, okay? But the detail on the activities, of the laboratory activities, will be part of a further discussion, okay? So we will talk about that later, okay, during the year, during the semester, okay? Good. Now, let's see some basics on the measuring chain. So let's start some general ideas about the course and about what you are going to do just once you are down in the laboratory. Okay, so let's see some basics, some very basic addressing on the measuring chain. So let me write that way. By the way, the course material will be complemented with these slides. Okay, so I will save that in a repository because we are using Google Meets. We are going to use Drive, that is the Google cloud storage place. Okay, it is practically limitless, so we can add whatever material we like. So I will create a sort of directory of the course in which I put all the material stuff there. Okay, and you can find them. Of course, I'll give you the link so that you are able to find them. So let me start talking about the basic addressing for the measuring chain. Of course, that is important because it is just the starting point of every experimental activity. So the question now is, how can I define a good measuring chain? How can I define a good measurement activity? Okay, we will enter into many details during the course, so don't worry about that. These are just a few remarks, very general. So don't expect now to be very precise in every point. It is just a general remark, a sort of general idea that you have always to follow. I always follow this general idea when I'm down in the laboratory for professional issues, okay? So first, you are going down in the laboratory for doing what? That is the first question. Measuring whatever, physical quantity. But are you measuring that blinded? Or you know what are you looking for? So the first point in your experimental activity is having a rough idea what you're looking for. Just to give you an idea, if I would like to characterize a temperature field inside a Ragan model, I would like to have temperature of about some 1,000, for example, degrees, not negative 100. Okay, I'm expecting sort of temperature. Okay, and that is very important because with this expectation, I am already thinking about the proper transducer, the proper measuring chain. I am expecting some result. My experimental activity is not fully blinded. I have to know what I'm looking for. Maybe you can find it. That is not sure, but maybe. Okay. If you don't know anything about that, whatever will be the outcome of your experimental activity is good for you. And maybe it is a lot of trash that you are having, just because you are completely wrong with the transducer, completely wrong with the analysis, completely wrong with everything, just because you don't know what you are measuring. Okay, so the first point here is what I call an a priori analysis sorry, not analysis, knowledge. And this knowledge could be analytical, numerical, okay, etc. Okay, of the range of values. Of the measurement quantities. Okay, just to have an idea, I know what I'm looking for. I know that I have to use a certain measuring chain with respect to other in order to maximize your output from the measuring activity. Then, if I need to consider some statistical analysis, I need to know what is the size of your data sets. 2 measurements is enough. 10 measurements is enough. 1 million measurements is not enough, for example. Okay, that's because you have to characterize with uncertainties, with averages, with RMS, with whatever statistical properties. Okay, so the point is to have an idea of the size of data sets for statistical analysis. By the way, you should know a priori if this statistical analysis is useful, it's meaningful for you. Oh, it doesn't have any meaning because you have just one shot. So no statistical analysis at all. Okay. So that's the reason why I'm using here if required. Okay. It is not always so that you need a statistical analysis, but if you need it, you have to know what is the minimum size of your data. Then, once you are down in the laboratory, what you have to do is a preliminary consistency analysis. Okay. Of your experimental data and try to apply possible data removal. Maybe you have a transducer that is not working well, is detached from your structure, for example. Okay, is completely broken. So this preliminary consistency analysis, it is giving you the idea that your measurement setup, your measuring chain is working well. Okay, not from the data point of view, but from the measuring chain point of view. Okay, so all the sensitivities are okay, the transducers are the good one, there are no broken transducers, connections and whatever effects is fully taken into account so that you are having a good measurement. Okay, if not, what happens? Stop the measurement? Not at all, because you are going to be paid to do that, for doing that. Therefore, you have to do some action. For example, if you have some broken transducer, if you have just one broken transducer out of many, then you can say, okay, I will remove that measurement because it will introduce trash in my good measurement. So I don't want to ruin my measurement. So, and I can't redo that again. So let's remove just that one. Okay. And that is just before doing the actual test. taking the actual measurement. Okay. If there are many transducer, many issues that will impair your measurements, then you have to stop and then try to solve the problem so that your activity will be giving us good results. Then, that is related with the previous point, evaluate, so the evaluation of the measurement uncertainty. Okay, and that could be done using the transducer uncertainty or using the statistical tools to associate your measurement with an uncertainty. Okay, that depends on your activity. But this evaluation of the certainty is, of course, one most important point. Then you have your data sets, you have the measurements, then your attention should be paid to correlate your experimental findings with the a priori options, with the a priori knowledge. Okay, so let's correlate. Okay, and that is your first check, because if you are expecting a certain value of the displacement, let's say millimeters, and from your measurement you find out that these displacements are of order of magnitude of meters, then there is a problem. Is that because of the sensitivity of your transducer? Is it because you are completely wrong in using the right transducer? Is it because there is something else that you are not considering, but is giving you that very different result from your a priori knowledge? Is your a priori knowledge wrong? Maybe you think to have millimeters, instead you are having meters. Okay, but however, you have to justify that difference. However, you have to have that your measurements are, let's say, in a good agreement with your a priori knowledge. Okay, because again, is you are expecting to have something, I have something, so everything is fine. Now it's a matter of the singular values. It's a matter of increasing the accuracy of the measurements. But the idea is there. Okay, if not, then I have to stop and think about that and try to change everything. Once you are okay also with that point, then the final consideration, that is a comparison. Of your experimental findings with reference data. Okay, and that is important. What are reference data? For example, paper that other colleagues had already published, for example, in different journal papers, okay, or other colleagues in other departments have already written a report, okay? So if I'm doing a certain static test on a typical structure and my colleagues 2 years ago made the same test and find out deflection of some millimeters, now I'm redoing that with something different and I'm obtaining deflection of some meters, maybe that's not good. Okay, maybe I can gain the Nobel Prize for that, maybe again kick out of the company right away. Okay, so that's the reason why once you have an idea, once your measurements are all, let's say, consistent with what you have, then you have to check what other people did in that field and see if you are there, if you are completely wrong, or actually if you are introducing something new. Okay, but you have to check that, you have to compare your results. Please, this sort of basic addressing for the measuring chain has to be always in your mind, starting from the report that you are going to do to take in your laboratory activities. Okay, because maybe your measurements are okay, but maybe there is something completely wrong that you can't see, and you spend nights try to justify in writing in your report that your result is good, but actually it's not. Just because you made a wrong setting in your sensitivity. So instead of having, let's say, meter, you have millimeters and vice versa. Okay, so please take care of these very, let's say, trivial things, but they are always there to be considered, and they are always giving you, let's say, some source of errors that are not very good to have from a professional. Okay. Having said that, now let's talk about what is the other component of your measurement chain, that is the data acquisition system. Okay, so you have a transducer, better, you have a problem. If you are doing testing, you have also the test specimen there, because you know a priori what are the measurements that you are expecting. You are defining sort of transducers, and then you need a data acquisition system. Of course, depends on the measurement type, depends on what you are doing now. But now let me talk with you about some general description about the data acquisition system, how it is, let's say, what are the general elements about it. Okay. The data acquisition system is having, of course, as the basic component is, of course, the transducer. Okay, that is, without that, you can have any measurement at all. Okay. What is a transducer? Let's start with the very basics. What is a transducer for you? Also for those at home, can you answer to this very easy question? Yeah, so the transducer is a device, whatever it be, that is working principle is based on different physical phenomena. We will see something about that. But the main characteristic is that it's capable to transduce, and that's the reason why the name, transduce that physical quantity into an electrical signal. Okay, and then we will use that electrical system, computer programs, whatever. Okay, so the basic, the transducer transduce a physical variable. Oh, sorry. To an electrical signal. Okay, and this electrical signal is feeding your data acquisition system. Okay, so your data acquisition system is receiving that electrical signal. Okay, so it received that electrical signal and then perform some tasks, okay, that are very useful for our analysis. What are these tasks? These tasks are, for example, collect data and produce a suitable output. Okay, for example, for my analysis. And this output could be, for example, an AD converter, an analog to digital converter, AD, could be a PC, could be whatever other thing. Okay. So that is what a data acquisition system is doing for us. Receive some electrical system that is characteristic of your physical quantity that has to be measured and gives out as output something that could be used for digital signal analysis, plotter, PC, whatever. Now, this data acquisition system is composed by three main elements. Okay, let's see them all. We have first an input stage. So I can write it there, 3 stages. The first one is the input stage. The second one is the conversion. And the third one is the output itself. Okay. Now, the input. Okay, the input is very easy. It is just the transducer. But I would add also some other items, transducers, amplifications, signal conditioning, filtering. Okay, just to name some options that you have when dealing with an output from your transducer. Okay, by the way, this amplification, condition, filtering will be part of a further analysis that we are going to have next in the course. Okay, and that is representing what is to me part of the first stage, that is the input stage of your data acquisition system. Most of the times you have to have this. Okay. Sometimes transducers have onboard part of the amplification, part of the conditioning, sometimes they do not have, and your data acquisition system is having for them. Okay. The problem, and therefore the idea of that, so the problem is that the output tension, the electrical signal coming straight from the transducer is characterized by very low values, a bit of noise, something that could be increased from the quality point of view of the electrical signal. And that's the reason why we are introducing the amplification, conditioning, filtering, okay? In order to have at the end of the input stage a good quality electrical signal that is truly representative of your physical variable that your transducer has just transduced. Then conversion. Conversion is very easy to see because, as I told you before, we are dealing with the analog to digital conversion, okay, because we are living in a digital world. So we have the analog to digital signal. Okay. And there are many properties, we will see that, and there are many problems and properties that we can consider when referring to this stage of your data acquisition system. And finally, the output. The output is very, very trivial also in this framework, because the output is just telling me that we are having, for example, the need to print out your whatever behavior. We have to use, let's say, PC, computer programs, okay, and so on, whatever. Your own programs that are capable to estimate the physical properties once you know that physical variable that you understand. So, and no direct property that could be estimated using direct property from your measured quantity. Okay. Computer programs. Okay. Now, just a question about the AD. Okay, so the digital digitalization of your system, and that's because we have many configurations. We have, if you want, there exists typically several measuring channels, and also so there exists several but also or several measuring chain. Okay, that are referring to different transducers, for example. Okay, and all belong to the same test that we are having. For example, we have to characterize the motion of the whole aircraft, of the whole space launcher in terms of both displacement, acceleration, temperature, field, and pressure. Okay, so we have all the things together. So we have many channels, measuring channels, and many measuring chains. Everything is going to feed your data acquisition system different way. Now the point is that the converter, the analog to to digital converter is something that is very costly, actually. Okay, because if you want something of high quality, you have to pay for it. Okay, so a way of reducing the cost, the overall cost of the acquisition system, is to use an analog to digital converter for all the measurements. The configuration of that is what we call a multi-sampling measuring chain or data acquisition system. And it works like that. Let's assume to have, for example, one transducer, transducer 1, transducer 2, and so on. We have many transducers. Okay, these transducers could be part of the same measuring chain or some other, okay, that are the same time the object of the measurement, but however, could be many transducers. And what we got is just an analog to digital converter that is used to transduce, to digitalize the signal transduced by transducers. In order to do that, we are adding here a block that is called scanner, that is asking to the different transducer what's the electrical value at different and known time stamps. Okay, so it is something like that. So what is done by the scanner is that time after time is asking the transducer what is their value. That information, of course, is passed to the AD converter, okay, in order to have the information required, okay? For example, we have here, or maybe we can think to, let me do that in this way. An amplification stage, okay, then we have an AD converter, okay, and then your output stage, as we already talked about. But the main important is that the scanner is having this information time after time. So if you require your signals to be synchronous, that is, you need to have the information of the different values of this transduced signal of your system, okay, at the same time, then you have to take care about the scanner, because if the scanner speed is high with respect to the time evolution of your signal, then you can assume that these values of the output quantities are synchronous. If the scanner speed is low with respect to the time evolution of your physical quantity measured by your transducer, then you can't assume that the acquisition is synchronous. That could be an issue or not, depends on you. Okay. The other option, of course, is that each transducer has its own AD converter. So no more scanning at all. Okay, so we are moving to a multiplex configuration. That is this one. Okay, to just a straight measurement that is formed by a transducer. Oops. Okay. Then we have the amplification stage, AG, and then whatever output stage. Okay, that is done for each transducer. So repeat that transducer 1, transducer 2, and so on. Okay, as you can see, we are having a lot of more components that are characterized in your data acquisition system with respect to the scanner one, with the multiplexing one. Okay. For example, when you are going down the laboratory for estimating your first model parameters, you can easily see by yourself that the data acquisition system is characterized by this last configuration. That is, each channel has its own analog to digital converter. Okay, and it costs a lot. Okay, and the cost is practically more than twice. Okay, than the other multiplexing system. And that, of course, depends on what is the refresh frequency of the scanner and so on. Okay, that's it. And by now, I think that time is over. Yes, we are okay. Any question for me? Any question from the audience at home? Okay, so see you tomorrow. Thank you for your passion about the systems that I got for my hardware. And
Thank you, Professor.
Thank you, you too. See you tomorrow, same times, and hopefully better hardware.
Professore, dove troviamo la registrazione, scusi?
La metterò piano piano su Drive.
Ok, va bene.
Vi darò a disposizione il link di Drive dove metterò le copie delle slide.
Ok, grazie mille, professore.
Datemi tempo. Bene.
Ok, grazie mille. Arrivederci.
Arrivederci. Termine l'elencazione. E questa abbiamo terminato. Come? No, raccoglie così, soprattutto non so come. Deve essere così. Ecco. Interrompi registrazione.